Tonight, we are going to talk about one of the most unsettling ideas in modern physics. What if the universe, all of it, everything you can see, everything that has ever existed, is the interior of a black hole, not a metaphor, not a thought experiment, a literal mathematical proposal, one that has been taken seriously by physicists for over 50 years, and one that, as of the last few years, has received its most intriguing observational support yet. From the most powerful telescope humanity has ever built, here's where it starts. There's a number. What we think we know about black holes. Let us begin with what a black hole actually is, because almost everything most people believe about them is either incomplete or wrong in an interesting way. The popular image of a black hole is a monster, a cosmic drain, a point of infinite hunger that tears apart everything that comes near it. Stars spiral in. Light disappears. Nothing escapes. It is the universe's most perfect trap, and somewhere at its center is a singularity, a place where the laws of physics break down entirely, where density becomes infinite, where space and time as we understand them simply cease to function. This image is not entirely wrong, but it is missing something crucial, and what it is missing changes everything. A black hole does not pull. That is the first thing to understand. Gravity always pulls, yes, but a black hole does not pull any harder than any other object of the same mass. If you replace the sun with a black hole of exactly the same mass, the Earth would not spiral in. It would continue orbiting exactly as it does now. The planets would not notice the difference, except for the loss of light and heat. The black hole would not reach out and grab anything. It would simply sit there, dark and cold, in the center of the solar system, and the universe around it would continue as before. What makes a black hole different is not the strength of its gravity, but the concentration of its mass. When enough mass is compressed into a small enough volume, space-time itself curves so severely that a boundary forms around it, a surface beyond which the curvature of space is so extreme that escape becomes geometrically impossible. Not practically impossible, not very difficult. Geometrically, mathematically, physically impossible, because beyond that boundary, every direction in space, including the direction that points away from the center, curves back inward. There's no path that leads out. The boundary itself is what we call the event horizon. The event horizon is one of the most remarkable concepts in all of physics, and it is worth sitting with for a moment. It is not a wall. There is nothing there. No barrier. No surface you could touch. If you were falling toward a black hole and crossed the event horizon, you would not feel it. There would be no jolt, no flash of light, no alarm. In fact, depending on the size of the black hole, you might not notice anything at all at the moment of crossing. The event horizon is not a thing. It is a threshold, a point of no return defined entirely by geometry, by the shape of space-time in that region. What makes it a boundary is not what is there, but what is no longer possible once you cross it. And this distinction between a boundary defined by physical substance and a boundary defined by geometric possibility turns out to be very important for the question we are asking tonight. The size of a black hole's event horizon is described by something called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who derived the solution in 1916. Remarkably, while he was stationed on the Russian front during the First World War, working out the mathematics of general relativity in the trenches. The Schwarzschild radius is simply the radius at which a given mass becomes a black hole. Compress any object to within its own Schwarzschild radius, and an event horizon forms. For the Sun, that radius is about 3 kilometers. For the Earth, it is roughly 9 millimeters, the size of a marble. For a human being, it is so small it cannot be meaningfully expressed without scientific notation. Most objects in the universe are nowhere near their own Schwarzschild radii. The Sun is nearly 1 million kilometers across, almost 300,000 times larger than its Schwarzschild radius would require. The Earth is 12,000 kilometers in diameter, far too large and diffuse to form an event horizon. This is why black holes are rare. They require extraordinary conditions. The gravitational collapse of the most massive stars, or the dense accumulations of matter at the centers of galaxies, to compress mass into the necessary volume. But here is where we have to slow down and look at a number that has been haunting cosmologists for decades. The number that started everything. In physics, when two quantities that should have nothing to do with each other turn out to be numerically equal or very close to equal, it is usually either a coincidence or a clue. Take the observable universe. The observable universe is not the same as the entire universe. It is simply the region of space from which light has had time to reach us since the Big Bang, approximately 13.8 billion years ago. Because the universe has been expanding this whole time, the observable universe today is a sphere roughly 93 billion light years across. Its edge is called the Hubble radius, after Edwin Hubble, the astronomer who first established that the universe was expanding. The Hubble radius is approximately 13.8 billion light years, though the precise figure depends on which measurement of the expansion rate you use, and this is itself a matter of active debate in cosmology. But for our purposes, the order of magnitude is what matters. Now, take everything inside the observable universe. Every atom in every star, every gas cloud, every planet, every black hole, every particle of dark matter we have inferred from its gravitational effects. Add it all up, the total mass energy of the observable universe, the total amount of stuff, is estimated at somewhere around 10 to the power of 53 kilograms. That is a number so large it has no intuitive meaning. It is roughly 100 billion trillion kilograms. Now calculate the Schwarzschild radius for that mass. Ask, if all that matter were compressed to the point of forming a black hole, how large would the event horizon be? The answer, and this is a number, is approximately 13.7 billion light years. That is almost exactly the size of the observable universe itself. The Hubble radius and the Schwarzschild radius of the observable universe are numerically close to the same thing. This is not a proven physical connection. Physicists are careful about this. It might be a coincidence. The universe contains just enough matter at just this density that the two numbers align. And there are technical reasons why the comparison is not quite as straightforward as it sounds. The Schwarzschild formula was derived for flat, static space-time, and our universe is expanding, dynamic, and curved in ways that require more careful treatment. So we should not simply announce that the universe is a black hole because the numbers match. That would be too fast. But we should notice. We should pay attention. Because in physics, numerical coincidences of this kind often turn out to be something more. They often turn out to be the first visible sign of a deeper connection, a thread that, when pulled, unravels something important. The physicist who first pulled this thread seriously was a man named Raj Kumar Pathria, the paper that nobody took seriously. In 1972, Pathria published a short paper in the journal Nature with the title, "The Universe as a Black Hole." It was, by the standards of what it was proposing, a remarkably calm paper. There was no sensationalism. There was mathematics and a question. The question was, given a numerical coincidence between the Hubble radius and the Schwarzschild radius of the observable universe's mass, might it be meaningful? Might our universe genuinely be the interior of a black hole belonging to some larger parent universe? The idea did not make a large splash. The physics community noted it, filed it, and largely moved on. The dominant framework in cosmology at the time was the Big Bang, and the Big Bang as a model was working beautifully. It explained the expansion of the universe, the cosmic microwave background radiation, the abundance of light elements. There was no obvious need for the additional architecture of a parent universe. Pathria's paper was interesting, but interesting in a way that many things are interesting, as a curiosity rather than direction. It would take another 2 decades and a different physicist working from a completely different angle to bring the idea back with something stronger behind it. That physicist was Lee Smolin, a universe that reproduces. Lee Smolin is a theoretical physicist based at the Perimeter Institute for Theoretical Physics in Waterloo, Canada, in 1992, and then more fully in a book called The Life of the Cosmos in 1997. He proposed something that went considerably beyond Pathria's numerical observation. He proposed that black holes do not merely resemble the origins of universes. He proposed that black holes are the mechanism by which universes reproduce. The argument goes like this. When a sufficiently massive star reaches the end of its life, it collapses. The outer layers explode in a supernova. The core, if it is heavy enough, continues collapsing past the point where electron pressure or neutron pressure can stop it, and a black hole forms. In the standard picture of general relativity, this collapse continues until matter reaches a singularity, a point of infinite density where the equations of physics produce infinities and break down. But Smolin proposed that we should not take the singularity literally. Singularities in physics, historically, have turned out to be signals that a theory is being applied outside its domain of validity, rather than genuine descriptions of physical reality. The singularity at the center of a black hole, he argued, is likely the place where general relativity breaks down and a more complete theory, a theory of quantum gravity, takes over. And in that more complete theory, the collapse does not continue to infinity. Instead, the collapsing matter reaches an extremely high but finite density, bounces, and begins expanding. What begins expanding, Smolin proposed, is a new universe. Not a universe embedded in our space. Not a universe somewhere else in our cosmos. A genuinely separate space-time, causally disconnected from ours, unreachable from our side, growing and expanding on the other side of what used to be a singularity. A baby universe born from the death of a star. And then Smolin added the element that makes this not just a creation story, but a scientific hypothesis. He proposed that each baby universe is born with physical constants slightly different from those of its parent universe. The speed of light, the mass of electrons, the strength of gravity, the value of the cosmological constant, these fundamental numbers, which in our universe seem finely tuned in ways we do not fully understand, will be inherited from the parent universe with small random variations. Some of those variations would produce universes with fewer black holes. Some would produce universes with more. The universes that produce more black holes would generate more offspring. Those offspring would in turn inherit parameters favorable to black hole formation, with further small variations. This is, Smolin pointed out, exactly analogous to natural selection. The universe evolves. Universes that are good at reproducing, that is, good at forming black holes, dominate the population. Universes that are poor at forming black holes leave fewer descendants. Over many generations of cosmological reproduction, the ensemble of universes becomes dominated by those whose physical parameters are optimized for black hole production. And here's the part of the argument that connects us directly. The physical conditions that make a universe good at forming black holes, heavy stars, long-lived stars, abundant carbon, stable atomic chemistry, turn out to be, roughly, the same physical conditions that make a universe hospitable to life. Not because life is a goal, not because the universe was designed with us in mind, but because both black hole formation and the evolution of life are favored by similar underlying physics. This is Smolin's hypothesis, known formally as cosmological natural selection. It is not mainstream physics. It has significant critics, and we will get the criticisms. But it is a serious scientific proposal from a respected physicist with mathematical structure and, in principle, the possibility of being falsified by observation. It is not a fringe idea. It is an open question. The problem with singularities. To understand why any of this is physically plausible, rather than just mathematically playful, we need to spend a moment with the singularity problem. General relativity is one of the most successful theories in the history of science. It has been tested to extraordinary precision. It correctly predicted the bending of light around massive objects, the existence of gravitational waves, the behavior of GPS satellites, the precise orbit of Mercury. In the 100 years since Einstein published it, not a single confirmed experimental violation has been found. But there are two places where general relativity produces predictions that physicists do not believe. Two places where the equations output infinities. Two places where the theory, almost certainly, is telling us not what is real, but where it reaches the limit of its own applicability. The first is the singularity at the center of black holes. The second is the singularity at the beginning of the Big Bang. In standard Big Bang cosmology, if you follow the expansion of the universe backward in time, everything gets denser and hotter. The galaxies converge, the matter compresses, the temperature rises without bound, and at time zero, at the beginning, you reach a singularity, a state of infinite density and temperature. General relativity predicts this, and general relativity almost certainly is wrong about it. The reason physicists are confident the prediction is wrong is not that they have a better answer. It is that infinite density is physically nonsensical. It means the theory has been pushed beyond its own valid range, when quantum mechanics is relevant. As it would be at the extreme densities of the Big Bang, general relativity does not apply. A theory of quantum gravity, one we do not yet have in complete form, is what would actually describe that regime. And in any plausible theory of quantum gravity, singularities are expected to be replaced by something finite, something physical, something that can be described without infinities. The most widely studied candidate replacement for the Big Bang singularity is the Big Bounce. The Big Bounce. The Big Bounce is not a single theory. It is a family of ideas developed within different approaches to quantum gravity that share a common feature. The beginning of our universe was not a singularity, but an extremely compressed but finite state from which the universe rebounded into expansion. The most developed version comes from a framework called loop quantum cosmology, developed primarily by Abhay Ashtekar and his collaborators at Penn State. Beginning in the early 2000s, in loop quantum cosmology, space-time itself has a fundamental quantum structure. It is not continuous but granular, made of discrete units at the Planck scale, which is roughly 10 to the power of negative 35 meters. Below this scale, space as a smooth continuum simply does not exist. In this framework, when matter is compressed to near-Planck densities, a new quantum repulsive force emerges from the granular structure of space-time itself. This force cannot be overcome by any amount of additional compression. It acts as an absolute floor. The collapsing matter reaches maximum density, roughly 5 times 10 to the power of 96 kilograms per cubic meter, a number so large it strains imagination, and then bounces. The universe that existed before the bounce, collapsing inward, becomes a universe we inhabit, expanding outward. This is the Big Bounce. Not an origin, but a transition. Not a beginning, but a turning point in a longer history. And here's where the connection to black holes becomes structurally elegant. If the Big Bounce is a correct description of our universe's origin, if we did not begin at a singularity but at a compression and rebound, then what caused that compression in the first place? What was the state before the bounce? What was collapsing? One natural answer, consistent with mathematics, is that what was collapsing was a region of a larger space-time that had exceeded its own Schwarzschild radius. In other words, a black hole in a parent universe, whose interior bounced into the expanding universe we now inhabit. This is not proven. Loop quantum cosmology is not a complete theory, and its extension from the cosmological context to the black hole interior context requires additional assumptions that remain under investigation. But it is a coherent, internally consistent picture. And it is the picture that an increasing number of theoretical cosmologists take seriously enough to study in detail. The event horizon from the inside. Let us pause and think about what it would actually mean to be inside a black hole. Not to fall into one, but to have been born inside one. To have spent your entire existence inside one, without ever having been outside. Most descriptions of black holes focus on the outside. You are far away. You watch something fall toward the event horizon. From your perspective, the falling object slows down as it approaches. Its light redshifts to invisibility. It appears to freeze at the horizon and then fade. The object has crossed the event horizon, but you never see it cross. The horizon, from the outside, appears as a membrane, the last surface from which light can escape. But from the inside, from the perspective of something that has crossed the event horizon, or something that was born on the other side, The situation is different. The event horizon is not a visible boundary. There is nothing to see. You cannot point to it. You cannot feel it. The light from outside does not show you a bright shell above you, because light from outside cannot get in. The event horizon is not a wall in space. It is a surface in space-time, a boundary that separates two causal regions. And once you are inside, you are simply inside. The universe you can observe, the one made of matter and light and galaxies, is your entire universe. This is a profound point. If our universe is the interior of a black hole, we would not expect to be able to see the event horizon. We would not expect to see the parent universe above us, pressing down. The event horizon is not a ceiling. It is a causal boundary, a limit of what can communicate with what. Everything inside the horizon, from our perspective, is the observable universe. Everything outside is, by definition, beyond our reach, beyond our observation, beyond even our ability to send or receive signals. We would not know we were inside a black hole, because everything we could ever know is defined by what is inside. And here's a deeply unsettling, or perhaps deeply calming, implication of that. The question of whether we are inside a black hole is not purely an empirical question, in the sense of go outside and look. There is no outside we can access. There is no experiment we can run that would allow us to step outside the observable universe and measure whether it is enclosed within an event horizon. The question must be approached indirectly, through theory, through consistency, through the internal logic of our best physical models, and, as we will see in the next part, through subtle observational signatures that might carry information about the universe's origin and structure. This is one of the reasons a hypothesis has been difficult to evaluate. It is not wrong because it makes no predictions. It is challenging because the predictions it does make are subtle, and because the alternative, the standard Big Bang singularity, also makes predictions, most of which have been confirmed to extraordinary precision. The black hole cosmology hypothesis does not replace or invalidate the standard model of cosmology. It proposes a different account of what came before the Big Bang, and a different mechanism for what produced the initial conditions we observe. On large scales, on the scales we can measure, the two pictures agree. Their differences lie precisely where our observations are weakest, the very beginning, the Planck density state, the first instance, what the universe looks like from the outside. There is one more angle worth considering before we close this first part, and it is a question of what our universe would look like from the outside if there were an observer in the parent universe watching the black hole that contains us. To that observer, our universe would look like any other black hole, a region of space-time from which nothing escapes, a dark sphere, possibly spinning, defined by its mass, its angular momentum, and its electric charge. It would not look like a universe from the outside. It would look like a black hole. This is not as strange as it sounds. We have no reason to think that the interior of a black hole should look like a black hole from the inside. We have no reason to think that the complexity, the structure, the billions of years of star formation and galaxy evolution and chemistry and biology that have unfolded inside our universe, we have no reason to think any of that will be visible or legible from the exterior. From outside, it is just a black hole. From inside, it is everything. The physicist Nikodem Poplawski at the University of New Haven has worked extensively on the mathematical details of this picture, using an extension of general relativity that includes a quantity called torsion, a property of space-time associated with the intrinsic spin of matter. In Poplawski's framework, the torsion of space-time prevents the formation of a true singularity inside a collapsing black hole. Instead, the matter reaches a maximum density and bounces outward, creating what is, from the outside, the interior of the black hole, and what is, from the inside, a new expanding universe. Poplawski's work is technical, mathematical, and specific. It is not a vague philosophical proposal. It is a set of equations derived from general relativity plus torsion that produce a quantitatively described bounce and expansion. The model makes predictions. Some of those predictions, as we will examine in detail in the second part of tonight's journey, have recently found unexpected observational support from data that were not designed to test this hypothesis at all. But that is for later. For now, let us simply sit with the question as it stands at the end of this first hour. The silence of the night sky. You are lying in the dark, above you or around you, depending on how you hold the geometry in your mind, is the observable universe. The cosmic microwave background, the faint afterglow of the hot, dense state that followed the Big Bang, presses in from every direction, almost perfectly uniform, cooled now to about 2.7 degrees above absolute zero. The galaxies are receding. The universe is expanding. It has been expanding for 13.8 billion years, and as far as our best measurements can determine, it will continue expanding forever. The galaxies growing farther apart, the stars aging and dying, the cosmos cooling toward a final, quiet equilibrium that cosmologists call the heat death, though that story is for another night. All of this, the expansion, the cooling, the formation of structure, the emergence of stars and planets and life, all of it is perfectly described by the standard model of cosmology, which has survived every observational test thrown at it. But the standard model does not tell us what happened before the Planck time. It does not tell us what happened before the singularity. It does not explain what gave rise to the initial conditions, why the universe started with a particular density, the particular entropy, the particular quantum fluctuations that seeded the galaxies we observe. These are not small gaps. They are the gaps at the very foundation of the story. Black hole cosmology does not fill these gaps with certainty. It fills them with proposal, a coherent, mathematically supported, not yet falsified proposal. That the universe began as the interior of a black hole, that the Big Bang was a big bounce, that the initial conditions we observe are the inherited properties of a collapse in a parent universe that we cannot see and will never reach. It is a proposal that changes nothing about the physics of daily life, nothing about the standard model's predictions on the scales we can test. But it changes everything about the story, about what the universe is, about what came before, about whether there's an outside or whether there's only this expanding interior, this everything we have ever known. In the next part, we will look at the evidence, the new data from the James Webb Space Telescope, the mathematical details of how a bouncing universe inside a black hole would leave its fingerprints on the cosmos we observe, the hypothesis of dark energy as the fading memory of a parent black hole's rotation, and the deep philosophical questions that arise when you take seriously the possibility that the universe is not the totality of existence, but one branch in an infinite, self-reproducing tree of space-times. The night is still long. The questions are still open. Rest here for a moment. There is more to come. There is something deeply human about the desire to find evidence, to not simply accept a beautiful idea because it is beautiful or a frightening one because it frightens us, but to ask, what would the world look like if this were true? What marks would it leave? What traces? What asymmetries? What patterns would appear in the data? Patterns that would not be there if the idea were wrong. This is a discipline of science, and it is harder than it sounds, because the universe is under no obligation to make its deepest truths easy to find. The signals can be subtle. They can be hidden inside measurements that were taken for entirely different purposes, analyzed years after the original observation, noticed by someone who was looking for something else entirely. The story of how black hole cosmology moved from philosophical curiosity to active observational science is a story of exactly this kind of patient, indirect detection. It is a story of telescopes pointed at the wrong question accidentally, finding an answer to a deeper one. It is a story of numbers that should not align, aligning, of symmetries that should not exist, existing. It is, in other words, the kind of story that keeps physicists awake at night, not from anxiety, but from a particular electrical alertness of a field that suddenly feels less settled than it did the day before. Let's begin with the most recent piece of evidence, the one that, as of early 2025, sent a hypothesis of black hole cosmology from the pages of specialist journals into the broader scientific conversation. Let us begin with the galaxies that are spinning wrong, the telescope that changed everything. The James Webb Space Telescope was launched on Christmas Day, 2021, and began its scientific operations in the summer of 2022. It is the most powerful astronomical instrument ever built by human beings, a mere 6.5 meters across, cooled to within a few degrees of absolute zero, operating in the infrared spectrum, capable of detecting light from galaxies that formed when the universe was less than 5% of its current age. The scientific community had high expectations for Webb. They expected it to refine our picture of early galaxy formation. They expected it to find new details in the cosmic microwave background's imprint on large-scale structure. They expected surprises, because every new generation of telescope delivers surprises, but surprises of a specific kind, refinements, corrections, details added to a picture whose broad outlines were already known. What they did not expect was evidence that the entire universe might have a preferred direction. In 2025, a study was published in the monthly notices of the Royal Astronomical Society by Leor Shamir, a computer scientist and astronomer at Kansas State University, who has spent years studying the statistical properties of galaxy rotation. Shamir's team analyzed images of more than 250 distant galaxies captured by the James Webb Space Telescope, some of the deepest, most detailed images ever taken of the early universe. They measured the rotation of each galaxy, which direction it was spinning relative to our line of sight. In a universe with no preferred direction, a universe that is, in the technical language of cosmology, isotropic, you would expect to find roughly equal numbers of galaxies spinning clockwise and counterclockwise. The distribution should be approximately 50-50. Any deviation from that would require an explanation, because there is no known mechanism in standard cosmology that should cause galaxies on opposite sides of the sky to prefer one direction of rotation over another. On the largest scales, the universe should be the same in every direction. This is one of the foundational assumptions of modern cosmology, built into the models, supported by decades of observations. Shamir's results showed something different. Approximately 2/3 of the galaxies in the sample were rotating in the same direction. The deviation from a 50-50 split was not enormous, but it was statistically significant, large enough that random chance was unlikely to be the explanation. Something, in the structure of the early universe, appeared to be influencing which way galaxies formed and rotated. The scientific response was, appropriately, cautious. A single study, even a careful one, is not a conclusion. The result would need to be replicated. The methodology would need to be scrutinized. Alternative explanations would need to be exhausted. And there are alternative explanations, observational biases, the difficulty of determining rotation direction from distant, faint images, the complexities of the particular galaxies in the sample. But here is what made the result impossible to simply set aside. It was not the first time this asymmetry had been observed. Shamir and other researchers had found similar hints in earlier data from ground-based telescopes. What the James Webb Space Telescope provided was a view so sharp, so deep, and so free from the distortions of Earth's atmosphere that the earlier hints became significantly harder to dismiss. And the Webb data pointed to the same direction as the earlier hints. The universe, if these observations are correct, has a preferred axis, a direction that is, in some subtle but measurable way, special. This is not predicted by standard cosmology. It is not part of the Big Bang model, as currently understood, and it demands an explanation. What could cause a spinning universe? Before we arrive at the black hole explanation, let us be fair to the full range of possibilities. Science proceeds by elimination as much as by inspiration, and there are several candidates for what might cause the kind of rotational asymmetry that Shamir's study identified. One possibility is observational bias. Galaxy rotation is determined from the pattern of light across a galaxy's face. The side spinning toward us appears slightly blue-shifted. The side spinning away appears slightly red-shifted. For distant, faint galaxies at the edge of Webb sensitivity, this measurement is difficult and subject to systematic errors. It is possible, not certain, but possible, that some systematic feature of the telescope, the instrument, or the analysis pipeline is producing an apparent asymmetry that is not real. Shamir and his collaborators have spent years trying to identify and eliminate such biases. They analyzed galaxies in different regions of the sky, observed at different orientations, processed through different pipelines. The asymmetry persists, but persistence across different analyses does not fully rule out systematic error. And until the result is independently confirmed by other teams using different instruments and entirely different methodologies, caution is warranted. A second possibility is that the asymmetry is real but local, a feature of our particular region of the universe rather than the universe as a whole. Large-scale flows of matter, gravitational perturbations from massive structures beyond our observable horizon, or simply the statistical clustering of galaxies with correlated formation histories, could potentially produce a local asymmetry without implying anything about the universe's overall structure. A third possibility, and this is where the physics becomes genuinely profound, is that the universe itself is rotating. Not that individual galaxies are rotating, which they obviously are, but that the entire universe as a system, as angular momentum, that space itself on the largest scales, is slowly spinning around some preferred axis. A rotating universe is not forbidden by general relativity. In fact, there exists a well-known solution to Einstein's field equations called the Gödel metric, discovered by the mathematician Kurt Gödel in 1949, which describes a rotating universe. Gödel was fascinated by this solution because it permitted closed time-like curves, paths through space-time that loop back to their starting point, meaning time travel would theoretically be possible in such a universe. Einstein was reportedly disturbed by this. Gödel, who was his close friend and colleague at Princeton, presented the solution to him as a birthday gift, in the spirit of gentle philosophical provocation. The Gödel universe does not match our observations in detail, and it is not what modern physicists mean when they discuss a rotating universe. But the point is that general relativity does not rule out cosmic rotation, and more recent work by Poplawski and others has examined rotating universe models that do match current observations, including the accelerating expansion we attribute to dark energy. And here is where the connection to black hole cosmology becomes not just elegant, but potentially explanatory. Poplawski and the rotating black hole. Nikodem Poplawski is a theoretical physicist at the University of New Haven, whose career has been devoted in large part to a very specific extension of general relativity. That extension involves a mathematical object called torsion. In standard general relativity, space-time has curvature. It bends in response to mass and energy, and that bending is what we experience as gravity. But in the more general mathematical framework that general relativity lives within, space-time can have another property beyond curvature. It can also twist. This twisting is called torsion, and in standard general relativity, it is set to zero, not because there's a physical reason set to zero, but as a simplifying assumption. When torsion is not set to zero, when you allow space-time to have this additional property. The theory is called Einstein-Cartan theory, named after Einstein and the French mathematician Elliot Cartan, who developed the framework in the 1920s. In Einstein-Cartan theory, the torsion of space-time is sourced by the intrinsic spin of matter, not the orbital spin of planets, not the rotation of galaxies, but the quantum mechanical property called spin that every fundamental particle possesses. Even electrons sitting perfectly still have spin. Even quarks inside a proton, going nowhere, have spin. In most situations, the spin source torsion is so small that it makes no detectable difference to any prediction. At the densities of ordinary matter, of stars, even of neutron stars, torsion is negligible. But the extreme densities inside a collapsing black hole, at densities approaching the Planck scale, 10 to the power of 96 kilograms per cubic meter, torsion becomes significant. And when it does, it produces a repulsive force that prevents matter from collapsing to singularity. In Poplawski's framework, this is what happens inside every black hole. The collapsing matter reaches maximum density. Torsion generates a bounce. The bouncing matter begins expanding from a perspective of the parent universe. This expansion is entirely contained within the black hole, hidden behind the event horizon, invisible, inaccessible. but from the perspective of the matter that bounced. It is a new universe, an expanding space-time, a new Big Bang, or more precisely, a big bounce. Poplawski's model makes several specific predictions about what this baby universe would look like. And those predictions are interesting precisely because they connect to observations we can actually make. The first prediction concerns the arrow of time. In Poplawski's model, matter crosses the event horizon of the parent black hole in one direction, inward. It cannot cross outward. This one-way flow, built into geometry of the event horizon, provides an asymmetry between the past direction and the future direction in space-time. This asymmetry, Poplawski argues, is inherited by the baby universe, the arrow of time in our universe. The fact that time flows in one direction, the fact that entropy increases, the fact that broken eggs do not spontaneously reassemble, could be, in this picture, a consequence of geometry of the event horizon through which our universe was born. This is a remarkable claim because the arrow of time is one of the deepest unresolved problems in theoretical physics. The fundamental laws of physics, quantum mechanics, general relativity, even thermodynamics at the microscopic level, are mostly symmetric with respect to time. They do not prefer one direction over another. And yet the universe we observe has a very strong temporal asymmetry. The past is different from the future. Entropy increases. Things break and do not reassemble. Why the universe has such a strong arrow of time when the fundamental laws do not require one is a question that has resisted explanation for over a century. Poplawski's answer is that the arrow of time is inherited from the parent universe through the geometry of the event horizon. It is not a property of our universe in isolation. It is a relational property, connecting us to the larger structure from which we emerged. The second prediction concerns rotation. Because black holes are formed from rotating objects, rotating stars, or material swirling into rotating galactic centers, they carry angular momentum. They spin, and in Poplawski's model, the angular momentum of the parent black hole is partially inherited by the baby universe. The baby universe has a preferred axis, the axis of rotation of the parent black hole, and this preferred axis influences the subsequent evolution of structure within the universe, including, Poplawski argues, the rotation of galaxies. When Shamir's 2025 results appeared, showing that 2/3 of galaxies in the deep web images rotate in a preferred direction, Poplawski was among the first physicists to comment publicly. His statement, reported by Space.com, was direct. He said that the simplest explanation for a rotating universe is that the universe was born in a rotating black hole. He said that a preferred axis in our universe, inherited from the rotation axis of the parent black hole, might have influenced the rotation dynamics of galaxies, creating exactly the kind of clockwise-counterclockwise asymmetry that Shamir's team observed. He was careful, as he should be, to note that these findings would need to be confirmed. The word he used was excited, not proven. A physicist's caution is not the same as skepticism. It is a recognition that a single study, however suggestive, is not the end of a question, but the beginning of a new investigation. But the alignment between prediction and the observation is striking. And it raises the question, if not black hole cosmology, what else would explain a preferred rotational axis in the universe? The dark energy connection. We have to talk about dark energy. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. In 1998, two independent teams of astronomers, led by Saul Perlmutter on one side and Brian Schmidt and Adam Rees on the other, discovered that distant supernovae were fainter than they should be if the universe's expansion were slowing down. The expansion was not slowing. It was speeding up. Something was pushing the universe apart, working against the gravitational attraction of all the matter within it. That something was named dark energy. Perlmutter, Schmidt, and Rees received a Nobel Prize in Physics in 2011 for this discovery, which remains one of the most important and most confusing results in modern cosmology. The problem with dark energy is that we do not know what it is. The simplest model, the one built into the standard cosmological model, designated as lambda in the equations, treats dark energy as a constant property of space itself, a uniform energy density that does not dilute as the universe expands but remains constant at every point in space-time, forever. This is a cosmological constant that Einstein originally introduced, discarded as a mistake, and then saw reinstated by observation. The model works. It fits the data. But it does not explain what the cosmological constant physically is, why it has the value it has, or why the value of vacuum energy density predicted by quantum field theory is roughly 10 to the power of 120 times larger than what we observe. A discrepancy so enormous that it has been called, without exaggeration, the worst prediction in the history of physics. Recent data, however, have added a complication. The Dark Energy Spectroscopic Instrument, known as DESI, began operations in 2021 and has been measuring the large-scale structure of the universe with unprecedented precision by mapping the positions of tens of millions of galaxies. In 2024 and 2025, DESI released results suggesting that dark energy may not be constant. The data hint, and it is still a hint, not a confirmation, that the strength of dark energy may be weakening over time, that whatever is accelerating the expansion of the universe is doing so less forcefully today than it did in the past. If confirmed, this would be one of the most significant results in cosmology in decades. A constant cosmological constant is already mysterious enough. A varying one is potentially more mysterious still, but also potentially more tractable, because a varying quantity is something that could have a physical source, a mechanism, a cause that changes with time. And Poplawski's rotating universe model offers, intriguingly, exactly such a source. In his framework, if a universe was born inside a rotating black hole and inherited that rotation, then the centrifugal effect of the universe's own angular momentum acts as an effective outward push. As the universe expands and its rotation slows, because angular momentum is conserved, and a larger universe rotating at the same angular momentum rotates more slowly, this centrifugal push also weakens. Dark energy, in this picture, is not a property of the vacuum. It is the fading mechanical effect of a spin that was impressed on our universe at its birth, from the rotation of a black hole in a universe we will never see. This prediction, that dark energy should weaken with time, is precisely what the early DESI results appear to show. To be absolutely clear, this is not a confirmed connection. The DESI results are preliminary. They are consistent with a weakening dark energy, but they are not yet definitive. Alternative explanations exist. Different models of dark energy, modified theories of gravity, systematic errors in the data, and Poplawski's rotating universe model is not the only model that predicts a time-varying dark energy. The match between the prediction and the DESI hint is suggestive, not conclusive, but it is the right kind of suggestive. It is a kind of match that warrants further investigation, where a theoretical prediction made on independent grounds finds an unexpected echo in observational data that was not designed to test it, the holographic principle and the surface of everything. There is another line of theoretical thinking that connects to black hole cosmology, one that comes from a completely different direction, from the study of information, thermodynamics, and quantum mechanics rather than from cosmology and general relativity. It begins with a question about entropy. In the 1970s, the physicist Jacob Bekenstein made a remarkable discovery about black holes. Working from the laws of thermodynamics, he proposed that black holes have entropy, and not just any entropy, but entropy proportional to the area of their event horizons, not the volume inside, the area of the two-dimensional surface that defines a boundary. This was initially puzzling, because entropy in physics is usually an extensive quantity. It scales with volume, not area. If you double the size of a box of gas, you roughly double its entropy. The entropy of a black hole breaks this rule. Make a black hole 8 times more massive, increasing its volume by a factor of 8, and its entropy increases only by a factor of 4, because the area of the event horizon scales as the square of the radius, while the volume scales as a cube. Stephen Hawking confirmed Bekenstein's insight when he derived, using a combination of general relativity and quantum field theory, that black holes radiate, that they emit thermal radiation at a temperature inversely proportional to their mass. This Hawking radiation, as it is now called, has never been directly observed. For black holes of astrophysical size, the temperature is so low that the radiation would be completely swamped by the cosmic microwave background. But its derivation is considered one of the most robust results at the intersection of quantum mechanics and gravity, accepted by the overwhelming majority of physicists as physically correct even without direct experimental confirmation. Hawking radiation carries information, or rather, the question of whether it carries information was one of the central debates in theoretical physics for decades. If a black hole evaporates completely through Hawking radiation, and if the radiation carries no information about what fell in, then information is destroyed. This would violate a fundamental principle of quantum mechanics, which holds that information is always conserved. This is the black hole information paradox, and it generated decades of fierce argument. The resolution, or rather, the most widely accepted current framework for thinking about the resolution, comes from the work of Gerard T. Hooft and Leonard Susskind in the 1990s. They proposed what has become known as the holographic principle, the idea that all the information about the interior of a region of space is encoded on its boundary, just as a three-dimensional hologram encodes a three-dimensional image on a two-dimensional surface. The interior is not independent of the surface. The surface is a complete description of the interior. This principle was given precise mathematical form by Juan Meldesena in 1997 in a result known as the ADS/CFT correspondence. Meldesena showed that a specific type of gravitational theory defined in a particular curved space-time, called anti-de Sitter space, is exactly equivalent mathematically to a quantum field theory defined on the boundary of that space-time, with no gravity at all. The two descriptions are different languages for the same physical reality. The ADS/CFT correspondence is one of the most important results in theoretical physics of the last 30 years. It has been used to calculate properties of quark-gluon plasma, to study strongly coupled quantum systems, to understand the thermodynamics of black holes. It is not just a speculative idea. It is a working mathematical tool with thousands of research papers built on it. And its implication for black hole cosmology is this. If the holographic principle is correct, then the information describing the interior of a black hole, the matter, the energy, the structure, the physics of everything inside, is encoded on the event horizon. The event horizon of the black hole that contains our universe would therefore be a surface encoding everything that our universe is and does. From the outside, a surface with information. From the inside, a universe. The holographic principle does not prove black hole cosmology. It does not tell us that we are inside a black hole, but it establishes something important, that the inside and the outside of an event horizon are related descriptions of the same reality, and that the distinction between inside a black hole and a universe may be less sharp than it naively seems. The mathematics does not clearly separate the two. The Big Bang singularity problem, revisited. Let us return to the problem of the singularity, because in the context of what we have been discussing, it takes on new weight. The standard Big Bang model, in its most basic form, describes a universe beginning from a state of infinite density and infinite temperature. As we said in the first part, this singularity is not believed to be physically real. It is where the theory breaks down, where quantum gravity takes over and general relativity ceases to be a reliable guide. But here is what is sometimes overlooked in popular accounts of cosmology. We do not know with any certainty what produced the initial conditions of the Big Bang. We do not know why the universe began with a particular entropy it had, an entropy so low, as Roger Penrose has calculated, that the probability of it arising by chance from a random initial state is a number so small it would require more zeros than there are atoms in the observable universe to write down. We do not know why the universe is so spatially flat, so close to the critical density that separates eternal expansion from eventual collapse. We do not know why the cosmic microwave background is so uniform across regions of the sky that, in standard Big Bang cosmology, could never have been in causal contact with each other. This last problem, the horizon problem, is typically addressed by cosmic inflation, a period of exponential expansion in the very early universe proposed by Alan Guth in 1980. Inflation stretches a tiny, causally connected region, the scales larger than the observable universe, explaining the uniformity. It also naturally produces a spatially flat universe and generates the quantum fluctuations that seed large-scale structure. Inflation is not confirmed by direct observation, but it makes predictions, particularly about the spectrum of fluctuations in the cosmic microwave background, that have been confirmed to high precision. Black hole cosmology offers an alternative to inflation that addresses some of the same problems. If our universe emerged from the interior of a black hole, the pre-bound state was already a highly ordered, causally connected region, a collapsing region of the parent universe that had been in contact, that had equilibrated, that had the low entropy appropriate for a highly compressed state. The uniformity of our cosmic microwave background is, in this picture, a natural consequence of the uniform initial conditions inherited from the collapse. The flatness of our universe is related to the geometry of the horizon. The small initial entropy is the entropy of a compressed but finite state rather than an infinitely improbable random initial condition. None of this has been worked out in complete detail. The connections are qualitative rather than fully quantitative. The hypothesis of black hole cosmology does not yet provide a complete replacement for inflation with precise predictions that can be tested. But it addresses the same questions from a different starting point, and it does so without requiring an additional, entirely separate epoch, inflation. That itself raises questions about what produced it and why it ended when it did. Lee Smolin's predictions and their problems. We need to return to Lee Smolin because his specific version of black hole cosmology, cosmological natural selection, makes sharper, more falsifiable predictions than the general framework, and those predictions have a complicated relationship with the available evidence. Smolin's core claim is that each black hole produces a baby universe with slightly different fundamental constants: the masses of particles, the strengths of forces, the value of the cosmological constant. The ensemble of universes is dominated, over many generations, by those whose constants maximize black hole production. Our universe exists in this ensemble, and therefore should have constants near optimally tuned for black hole production. This is a testable claim. If you changed any of the fundamental constants of our universe by a small amount, the theory predicts that the number of black holes produced in the resulting universe should decrease. Smolin explicitly issued this as a challenge to the physics community. Find a small change to any fundamental constant that would increase black hole production, and you falsify the theory. The results of that challenge have been mixed. On one hand, some of the constants of our universe do appear to be near optimal for production of stellar mass black holes. The mass of the proton relative to the electron, the strength of the strong nuclear force, the initial conditions that produce long-lived stars. These do seem to be in a regime that favors black hole production. On the other hand, critics have pointed out potential counterexamples. The cosmological constant, for instance, the same dark energy we've been discussing, could, in principle, be increased without obviously decreasing black hole production, and in some analyses might even increase it. Alexander Vilenkin of Tufts University made this argument in a technical paper, suggesting that increasing the cosmological constant up to a point would speed expansion in a way that could facilitate more black hole formation. Smolin has contested these criticisms, arguing that they rely on assumptions about physics beyond the standard model that are not well established. The debate is ongoing and unresolved. A more fundamental challenge to Smolin's specific version of the hypothesis was raised by Leonard Susskind and others in the context of black hole information theory. Smolin's mechanism requires that some information about the parent universe's physical constants be transmitted to the baby universe. Otherwise, the constants of the baby universe would not be related to those of the parent. But the current consensus in quantum gravity, building on the work of Hawking, Page, Meldacena, and others, is that information is not lost in black holes. Information that falls into a black hole is eventually returned, encoded in the Hawking radiation. It does not pass through to a baby universe. If this consensus is correct, the specific mechanism Smolin proposed, parameter transmission through the singularity, does not work. Smolin has acknowledged his challenge as serious. His response has been that the alternative, full information preservation with no baby universe connection, depends on assumptions about quantum gravity that are themselves not established. In the Einstein-Cartan framework that Poplawski uses, where there is no singularity because torsion prevents it, the information question takes a different form. The geometry of the bounce is not the same as the geometry of the singularity, and the conclusions derived from singularity physics do not straightforwardly apply. This is a genuine technical debate among physicists, not a case of laypeople misunderstanding what scientists have settled. The information paradox, despite years of progress, remains an area of active research. The question of what happens to information inside a black hole, does it return in Hawking radiation? Does it pass to a baby universe? Does it do something else entirely? Is still open. What is appropriate to say is this. Smolin's specific version of the hypothesis faces serious challenges from the direction of information theory. The more general version, that our universe began as the interior of a black hole, that the Big Bang was a bounce from a black hole collapse, that we are living inside an event horizon, does not depend on Smolin's specific information transmission mechanism, and is not directly undermined by the information paradox arguments. The family of ideas called black hole cosmology is larger than any single physicist's version of it. What the numbers say. Let us collect the quantitative observations that bear on this hypothesis, because it is worth seeing them together. First, the Hubble radius of the observable universe, approximately 13.8 billion light-years, is numerically close to the Schwarzschild radius corresponding to the total mass energy of the observable universe. This was Path 3's original observation in 1972, and it remains striking. It does not prove that we are inside a black hole, because the Schwarzschild radius formula is derived for a static, non-expanding space-time, and our universe is neither static nor non-expanding. But the approximate numerical coincidence is, at minimum, consistent with the hypothesis. Second, the James Webb Space Telescope's observation that approximately 2/3 of deep-field galaxies rotate in a preferred direction, published in 2025. If confirmed by independent analysis, this implies that the universe has a preferred rotational axis. Standard cosmology does not predict this. Black hole cosmology, specifically in a version where our universe was born inside a rotating black hole, predicts exactly this. Third, the early DESI results suggesting that dark energy may be weakening over time. Standard cosmology, with a constant cosmological constant, does not predict this weakening. A rotating universe model, in which the effective dark energy comes in the fading centrifugal effect of inherited angular momentum, predicts that dark energy should weaken as the universe expands and slows. The current DESI data are consistent with this prediction, though not yet definitive. Fourth, the uniformity of the cosmic microwave background. The fact that the universe looks essentially the same in all directions, to 1 part in 100,000, which is explained in the standard model by inflation, but which could also be explained by the causal connection of material collapsing into a black hole before the bounce. Fifth, the spatial flatness of a universe, which is explained in the standard model by inflation, but which is also a prediction of certain black hole cosmology models, in which the geometry of the horizon imposes a specific curvature on the interior. None of these observations, individually, confirms the hypothesis, but they are all consistent with it. And a combination of numerical coincidence, observational alignment, and theoretical coherence is enough to make the hypothesis something that serious physicists take seriously, not as a proven fact, but as a live possibility that warrants sustained investigation. What would change if we are inside a black hole? Before we move into the philosophical territory that will occupy the final part of this journey, let's ask the practical question. If it turned out to be true, if we genuinely are living inside a black hole, what would change? Physically, nothing. The stars would continue to burn. The planets would continue to orbit. The atomic physics that governs chemistry, biology, and thought would be unchanged. The fact that we are inside an event horizon does not affect any interaction within that event horizon. The event horizon is not a physical constraint on what can happen inside. It is a constraint on what can communicate with the outside. Since we cannot communicate with the outside regardless, our inability to do so is simply confirmed rather than newly imposed. For the practice of cosmology, something significant would change. The question of initial conditions, why the Big Bang started the way it did, would gain a potential answer. The fine-tuning of physical constants would gain a potential explanation, either through Smolin's natural selection mechanism or through some other inheritance process. The arrow of time would gain a potential origin. Dark energy would gain a potential source. For physics as a whole, the implications would be profound. We would have a model, not yet a complete theory, but a framework for how universes are created, how their properties are determined, how they are related to each other. We would have a mechanism for what came before the Big Bang, and that mechanism would connect our universe to a larger structure of nested spacetimes for human beings. For the question of what we are and where we came from, the implications are harder to characterize. We would be living not in a universe, but in a universe, one among potentially countless others, each born from a black hole, each containing its own stars and potentially its own life, and its own beings looking up at their own night sky and asking their own version of the same question. The cosmos would not be less wondrous for this. It would be larger, it would be deeper, it would contain, nested within itself, an infinity of interiors, each one a world, each one complete, each one unable to reach the others. That is not a reduction of meaning. That is an expansion of it. The open door. Science does not close doors prematurely. It is not in the nature of science to declare a question settled before the evidence is truly definitive. And the question of whether our universe is the interior of a black hole is not settled. What we have, at the end of the second part, is a constellation of observations and theoretical arguments that are consistent with the hypothesis, that in some cases are specifically predicted by the hypothesis, and that do not yet have definitive alternative explanations. We have an old numerical coincidence that refuses to be dismissed. We have new telescope data that should not exist under standard cosmology. We have a theoretical framework built from well-established physics, general relativity, quantum field theory, thermodynamics, that makes the hypothesis coherent rather than merely imaginative. And we have a growing community of physicists who are taking it seriously enough to publish about it, to test it, to argue about it, to refine it. That is where good science lives. In the space between established fact and open question. In the tension between what we know and what we have not yet figured out. In the third and final part of tonight's journey, we will go somewhere different. We will leave the data and the equations behind, not to abandon rigor, but to sit with the implications. What does it mean for a universe to have a parent? What does it mean for a consciousness to exist inside an event horizon? What does it mean for human life and human thought and human aspiration that the cosmos itself may be, in the deepest sense, a closed room? These are not questions with answers in the usual sense, but they are questions worth asking. And the night is still long enough to ask them, a moment of stillness. There is something that happens when you've been thinking about very large things for a long time. The thoughts begin to settle. The intellect, which has been busy gathering and connecting and evaluating, slows a little. And what remains is not the absence of thought, but a kind of open attention, a quiet readiness to simply hold the scale of what you've been considering without needing to immediately do anything with it. We have covered enormous ground tonight. We have gone from the surface of a dark planet to the event horizons of black holes, to the birth of universes. We have followed observations from the deepest images ever taken by a human instrument to the mathematical structures of quantum gravity. We have visited the ideas of physicists who have spent decades on these questions. Pathria, Smolin, Poplawski, Bekenstein, Hawking, Meldesena, and we have tried to hold their work honestly, to mark clearly what is confirmed and what is hypothetical, what is widely accepted and what is contested. And now, in the space between this part and the next, let the scale of it rest for a moment. You are possibly inside a black hole, the universe you inhabit, the stars, the dark matter, the ancient light of the cosmic microwave background, the galaxy spinning in a preferred direction. All of it may be contained within an event horizon in a larger space-time. you will never observe. The Big Bang may have been a bounce. The arrow of time you experience may be an inheritance from that larger universe. The dark energy slowly loosening the bonds between galaxies may be the diminishing rotation of a dead star's collapse, echoing forward through 13 billion years. Or none of this may be true. The coincidences may be coincidences. The asymmetry in galaxy rotation may be an artifact. The DESI hints may resolve into a constant cosmological constant after all. The universe may have begun as a singularity, and everything we observe may be adequately explained without the architecture of nested spacetimes. We do not yet know. That is the honest answer, and it is also, in its own way, the most interesting answer, because not knowing that we do not know, knowing why we do not know, understand the shape of our ignorance, is where the next discovery begins. There is a certain kind of question that science cannot answer by pointing. The most important questions, the ones that reach past the boundary of what is observable, past the event horizon of the knowable, must be approached differently, not with less rigor, but with a different kind of rigor, with careful reasoning about what follows from what, with attention to which conclusions are inevitable and which are merely possible, with the honesty to say at the edge of the map, here the territory continues, but we have not yet seen it. We have traveled a long way tonight. We began with a dark field of stars and a question that most people have never heard asked seriously. We followed it through the mathematics of event horizons and Schwarzschild radii, through the equations of loop quantum cosmology and the Einstein-Cartan extension of general relativity, through the images from the deepest telescope ever built and the hints in the galaxy rotation data that arrived in 2025 and that the community is still working to understand. Now we arrive at the final territory, the territory where physics and philosophy meet. Not because we have run out of physics, but because the physics itself raises questions that physics alone cannot close. What kind of universe is this? If this idea is true, what does it mean? What changes and what is not? The horizon as the limit of knowledge. Let us begin with what is perhaps the most unsettling implication of the hypothesis, and get it on the table clearly. If we are inside a black hole, if the boundary of the observable universe corresponds, in some meaningful sense, to an event horizon, then there is a category of questions we cannot, even in principle, answer by observation. Not because our instruments are too small, or our mathematics too undeveloped, or our civilizations too young, but because the structure of space-time itself forbids irrelevant signals from reaching us. The event horizon is not a barrier we might one day cross with better technology. It is a causal boundary defined by the geometry of space-time. Information from outside cannot travel inward across it. We cannot receive any signal from the parent universe. We cannot send any signal there. We cannot, by any physical means, confirm or deny the existence of the larger structure within which our universe might be embedded. This is a hard limit, and hard limits are uncomfortable for science, which depends on the possibility of testing ideas against the world. But before we conclude that the hypothesis is therefore unscientific, we should be precise about what this limit does and does not prevent. It does not prevent us from testing the consequences of the hypothesis within our universe. If our universe was born inside a rotating black hole, that birth should have left imprints, a preferred rotational axis, a specific pattern of initial conditions, a particular behavior of dark energy over time. These are observable, at least in principle. We have already discussed several of them. The fact that we cannot reach the parent universe does not mean the hypothesis makes no predictions we can test. The physicist Carlo Rovelli, who works on loop quantum gravity at the Centre de Physique Théorique in Marseille, has written carefully about the epistemological status of ideas at the edge of observability. His position, broadly, is that a hypothesis can be scientifically meaningful even if its most direct implications lie beyond direct observation, provided that it connects coherently to things we can observe and that its alternatives make different predictions about those same observable things. Black hole cosmology meets this criterion, at least in principle. It is not unfalsifiable in a way that a purely metaphysical claim is unfalsifiable. It is rather indirectly falsifiable, which is also how we test most of what we know about the early universe, about quantum gravity, about dark matter, what cannot give us a certainty. And this is the first thing that the hypothesis asks us to come to terms with. At the deepest level of cosmological truth, certainty may not be available. The philosopher Immanuel Kant, writing more than 2 centuries ago, distinguished between the world as we can experience it, the phenomenal world bounded by our categories of perception and cognition, and the world as it is in itself, the noumenal world, which lies forever beyond direct access. He thought this limit was a feature of human minds. It may turn out to be a feature of the universe's geometry. The event horizon is not a prison wall. It is the edge of the knowable. And there is a difference, a philosophically significant difference, between a prison and a home. A prison is a place whose walls constrain you from reaching somewhere better. A home is a place that contains everything you have and love. The walls of a home are not constraints. They are simply the shape of where you live. If we are inside an event horizon, we are not imprisoned. We are located. Everything we have ever known, everyone who has ever lived, every thought that has ever been thought, every photon of light that has ever illuminated any eye, all of it is inside this boundary. The boundary is not a tragedy. It is simply the geometry of our situation. Fractals all the way down. The second implication worth considering is the one that sends the imagination farthest, and which must be approached with the most care. If our universe was born inside a black hole, and if our universe contains black holes, which it does by the billions, in the centers of galaxies and scattered throughout space as the remnants of collapsed stars, then, if the logic holds symmetrically, each of those black holes may contain a universe of its own. This is the fractal structure implied by the hypothesis in its most general form. Each universe contains black holes. Each black hole may contain a universe. Each of those universes contains its own black holes. And so on in both directions. We're inside a universe that may be inside a black hole that is inside a universe that may be inside a black hole, a nesting of space-times extending outward without end and inward without end. It is worth noting carefully what this claim is and what it is not. This is not the multiverse of some versions of string theory, where infinitely many universes coexist in the same space, differing by their vacuum states. It is not the many worlds interpretation of quantum mechanics, where every quantum measurement branches a universe into parallel histories. It is a different structure entirely, a hierarchical nesting of causally disconnected space-times, each contained within the other, like an infinite set of Russian dolls, each one sealed from all the others. The physicist Nikodem Poplawski has described this picture explicitly. In his Einstein-Cartan framework, every gravitational collapse produces a new space-time region. Not in our universe, not connected to our universe, but genuinely separate. Our universe is one such region. The black holes we observe are the seeds of others. The black hole that produced our universe is itself inside a parent universe that may have its own parent. Now, are those child universes of ours real? Do they exist? Here we must be absolutely honest about the limits of what we can say. Poplawski's mathematics describes such regions as physically real, as genuine space-time manifolds, with matter and energy and potential with their own galaxies and stars, and perhaps their own forms of complexity. But we have no way to interact with them, no way to confirm their existence by any direct measurement. The prediction that they exist is a consequence of a theoretical framework, not an independently testable fact. What can be said is this: if the hypothesis is correct, and if the mathematics of Einstein-Cartan gravity describes the physics of black hole interiors correctly, then the universe we observe is not the universe in its entirety. It is one room in an infinite house, a house whose other rooms we will never enter and cannot see. This is not a scientific conclusion. It is a scientific inference, a statement about what would follow if certain theoretical frameworks are correct, and the appropriate response is neither to enthusiastically embrace it nor to dismiss it, but to hold it as a genuine open possibility, while continuing to test the frameworks that imply it. There is, however, one aspect of this fractal picture that is worth sitting with, simply because of what it implies about the status of our own universe. If each of the billions of black holes in our observable universe is the seed of a new space-time, and if each of those space-times contains its own galaxies and black holes, then the number of space-times generated by our universe alone is staggering. And our universe, from outside, is just one of countless black holes in a parent universe. The picture is not lonely. It is, in a certain sense, profoundly populated, a cosmos of cosmoses, each complete in itself, each containing its own long story. Whether or not that is true, the contemplation of it does something interesting to the sense of scale that most people carry around with them. The universe already seemed impossibly large, 93 billion light-years across, containing perhaps 2 trillion galaxies. The fractal picture makes that entire expanse a single room, and it makes our galaxy a modest spiral, one of hundreds of billions, a room within that room, and our solar system a corner of that galaxy, and our world a speck in that solar system. And yet here we are, asking the question, the problem of falsification. The question of whether black hole cosmology is a scientific hypothesis in the strict sense, whether it is, in Karl Popper's formulation, falsifiable, is one that requires a careful answer rather than a quick one. Popper's criterion, developed in the early 20th century, holds that a hypothesis is scientific if and only if it makes predictions that could, in principle, be shown to be false by observation. A claim that cannot be disproved by any possible evidence is not a scientific claim. It is a philosophical or metaphysical one, which may or may not be true, but which science has no tools to evaluate. By this strict criterion, the question of whether we are inside a black hole faces a genuine challenge. The most direct prediction of the hypothesis, that there is an event horizon bounding the observable universe and a parent universe on the other side, is not falsifiable in the standard sense, for the reasons we have discussed. No observation can reach beyond the event horizon. No experiment can detect the parent universe. The most central claim of the hypothesis lies, structurally, beyond the reach of empirical test. But here we need be precise, because the hypothesis is not monolithic. It is a family of related ideas with different levels of specificity, and different parts of that family have different relationships to falsification. The most general claim, that the universe began from a highly compressed, bouncing state rather than a true singularity, is consistent with loop quantum cosmology and other quantum gravity frameworks, and may eventually be testable through signatures in the primordial gravitational wave background. The future gravitational wave observatories, including the proposed Laser Interferometer Space Antenna, or LISA, and the Einstein Telescope, a third-generation ground-based detector, may be sensitive enough to detect the characteristic imprint of a pre-bounce phase on the spectrum of primordial gravitational waves. A bounce from a black hole interior would leave a specific pattern of gravitational wave signals that differs, in calculable ways, from the pattern produced by standard inflation. This is a genuine, in principle falsifiable prediction. The specific rotational claim that the universe inherited angular momentum from a parent rotating black hole, and that this inheritance manifests as a preferred rotational axis for galaxy formation, is also falsifiable, and its falsification is actively underway. If independent analyses of the JWST data, using different methodologies and different galaxy samples, fail to reproduce Shamir's asymmetry, that would not falsify the entire hypothesis, but would remove one of its current observational supports. The result needs replication. The scientific community is actively working on it. The dark energy prediction, that if the universe's rotation is the source of the observed cosmic acceleration, then the effect of dark energy should weaken over time as the universe expands and slows, is testable by the DESI survey and by the next generation of large-scale structure surveys, including the Euclid Space Telescope, which began operations in 2023. If the DESI hints of weakening dark energy solidify into a confirmed measurement, that would be a significant point in the hypothesis's favor. If DESI and Euclid find that dark energy is truly constant, that would be a point against one important version of the rotating universe prediction. Lee Smolin's specific version of the hypothesis, cosmological natural selection, faces the deepest falsifiability challenge. As the philosopher of physics Tim Maudlin and others have noted, Smolin's central claim that our universe is near optimal for black hole production requires the auxiliary assumption that our universe is typical among all possible universes. Without that assumption, any observation can in principle be accommodated if our constants do not appear optimal for black hole production. The theory can be saved by arguing that our universe is atypical. This retreat is always available, which means the central claim is, at best, very difficult to falsify and, at worst, genuinely unfalsifiable. Smolin has pushed back against this criticism, and the debate continues in the literature. What is fair to say is that cosmological natural selection, as currently formulated, has the structure of a hypothesis that could be sharpened into something more clearly falsifiable, but has not yet been sharpened to that degree. It is a work in progress, scientifically speaking, and should be held as such. The broader family of black hole cosmology ideas, the bounds, the event horizon as cosmological boundary, the inherited initial conditions, exist in a space where some predictions are testable and some are not. This is not unusual in frontier physics. Aspects of string theory, cosmic inflation, and the many worlds interpretation of quantum mechanics all share this partial falsifiability structure. The appropriate response is not to dismiss the untestable parts, but to pursue the testable ones with rigor and to maintain epistemic clarity about which parts of the framework are supported by evidence and which are held by theoretical consistency or philosophical preference. What would it take to seriously strengthen the case for black hole cosmology? Several independent lines of evidence would need to converge. Confirmation of the galaxy rotation asymmetry by multiple independent teams, using different instruments and different analysis methods. A confirmed measurement of weakening dark energy, consistent with a time-varying signal rather than a constant cosmological constant. The detection of pre-bounced signatures in the primordial gravitational wave background, distinguishable from inflationary predictions, and theoretical progress. The development of a more complete quantum gravity framework that clearly describes the physics of the black hole interior, the bounce, and production of the universe we observe, with quantitatively precise predictions rather than qualitative arguments. None of these alone would be definitive, but their combination, multiple independent observations pointing in the same direction, supported by a coherent theoretical framework, would constitute a scientific case that the community would take very seriously indeed. That case does not yet exist. What exists is a cluster of hints, a coherent framework, and an open question. What remains unchanged? There is a question that arises naturally when you spend a long time thinking about the hypothesis that the universe is inside a black hole. The question is, does any of this matter? Not in the philosophical sense. Clearly it matters philosophically. Clearly it matters for our understanding of what the cosmos is. But in the practical, day-to-day human sense, if this were true, what would be different about Monday morning? The answer is nothing. The stars would still burn by nuclear fusion, converting hydrogen into helium at temperatures of tens of millions of degrees. Planets would still orbit according to Kepler's laws. Water would still freeze at 0 degrees Celsius at sea level and boil at 100. DNA would still replicate, imperfectly and beautifully, producing the variation on which natural selection acts. Neurons would still fire in the patterns that constitute thought, memory, love, and grief. Children would still be born, and the people who love them would still feel a particular overwhelm of that love. None of the physics that governs any of these things cares whether there is an event horizon at cosmological scales. The event horizon, if it exists, is not a force or a field or a substance. It is a geometric property of space-time at scales far beyond anything that affects the interactions of ordinary matter. It is simply there the way the curvature of the Earth is there beneath us. Present, real, but not impinging on experience of walking down a street. This is worth saying carefully, because there is a tendency, in popular accounts of cosmology and physics, to treat large-scale discoveries about the nature of the universe as destabilizing. As if learning that the universe is larger than we thought, or older, or stranger in its geometry, should make us feel smaller or less certain, or somehow threatened. as if the discovery that we might be inside a black hole is a kind of bad news. It is not bad news. It is information. The stars are still real. The warmth of another person is still real. The long, improbable history of life on this planet, the bacteria that first exhaled oxygen, the fish that first found legs, the hominids who first looked up and pointed at the light and wondered, all of that happened and is real, regardless of what the boundary conditions of the universe turn out to be. Roger Penrose, the British mathematical physicist who shared the 2020 Nobel Prize in Physics for his work on black holes, has written and spoken extensively on the relationship between cosmological theory and human meaning. His view, broadly, is that the mathematical structures through which the universe expresses itself are not indifferent to consciousness, that the fact of understanding or perception of a universe that can model itself for the minds of its inhabitants is itself something worth taking seriously as a feature of reality. You do not have to accept Penrose's specific philosophical positions to recognize the point he is gesturing at. The capacity to ask the question, are we inside a black hole, is not diminished by the possibility that the answer is yes. It is, in fact, a remarkable example of the universe turning its attention on itself. We are, as far as we know, the only form of matter in the observable universe that asks questions about the observable universe. Whether we are inside a black hole or not, that fact is extraordinary. The evolution of everything you can see. There is one more thing to say about what remains unchanged, and it concerns time. The universe has a history. It has been 13.8 billion years since the Big Bang. Or, if the black hole cosmology hypothesis is correct, 13.8 billion years since the bounce that we call the Big Bang. In those 13.8 billion years, a great deal has happened. The first atoms formed 380,000 years after the bounce, when the universe cooled enough for electrons to settle into orbits around nuclei. The first stars ignited a few 100 million years later, in the darkness of what cosmologists call the cosmic dark ages. Those first stars were enormous and short-lived, burning through their hydrogen in millions of years rather than billions, and dying in supernova explosions that seeded the universe with the heavy elements, carbon, oxygen, nitrogen, iron, that all subsequent chemistry and all subsequent life would require. Stars formed and died. Galaxies assembled. The heavy elements accumulated in each generation of stars, enriched by the products of earlier stellar deaths. The universe was, and is, a long, slow process of increasing chemical complexity, driven by the fusion fires of stellar interiors and the explosive deaths of massive stars. Our own sun is a third-generation star, formed from gas that had already been through at least 2 previous cycles of stellar birth, nuclear burning, and death. The carbon in your body was forged inside a star that died billions of years before the sun existed. The iron in your blood came from a supernova. You are, in the most literal and non-metaphorical sense possible, made of the process remains of dead stars. None of this changes if we are inside a black hole. The stellar physics is the same. The nucleosynthesis is the same. The long chain of cosmic events that produce the conditions for chemistry, and for biology, and for you, reading this, is the same. What might change is the interpretation of why these conditions exist. Why does our universe have the particular physical constants that permit stars to shine for billions of years, rather than millions? Why does it have a carbon resonance level, the Hoyle state, predicted by Fred Hoyle and confirmed in the 1950s, that allows carbon to form efficiently in stellar interiors? Why are the fundamental forces balanced in the way they are, so that atoms are stable, so that chemistry is possible, so that the long, patient work of natural selection has time to operate? These questions are often grouped under the heading of the fine-tuning problem. Our universe appears to have been configured with remarkable precision in ways that allow complexity to develop. Adjust a strong nuclear force by a few percent, or the mass ratio of the proton to the electron, or the value of the cosmological constant, and the universe either collapses too quickly for galaxies to form, or expands too fast for gravity to gather matter into stars, or burns out in a few million years, or never produces the elements beyond helium. Why? The standard answer in most versions of modern cosmology is that we have no answer, We simply find ourselves in a universe that has these properties, and the fact that we exist to ask the question is itself evidence that the universe has properties compatible with our existence. This is the anthropic principle in its weak form, and it is more tautology than explanation. Smolin's cosmological natural selection offers a different answer. Our universe has these properties because universes that lack them produce fewer black holes, and therefore fewer descendant universes. Over the evolutionary history of the multiverse, the population comes to be dominated by universes with constants that maximize black hole production, which happen, approximately, to be the constants that allow long-lived stars and complex chemistry. Our existence is not a coincidence. It is a consequence of selection process operating at the level of universes. This answer has the virtues and the problems we discussed in the previous part. It is elegant. It is not yet fully falsifiable. It is taken seriously by some physicists and criticized seriously by others. But even if Smolin's specific mechanism is not correct, the black hole cosmology framework raises the fine-tuning problem in a new way. Rather than asking, why do these constants have these values? It asks, where did our universe inherit its constant from? And opens the possibility that the inheritance itself is the answer, not a random draw from all possible values, not a design, but a transmission from a parent universe, with the small variations and long-term selection dynamics that Smolin described. Whether that answer is correct, we do not yet know. The long silence before an answer. There are questions in science that remain open for decades before the evidence arrives to settle them. The existence of the Higgs boson was predicted in 1964 and confirmed in 2012. 48 years of theoretical confidence waiting for experimental proof. Gravitational waves were predicted by Einstein in 1916 and detected in 2015, 99 years. The cosmic microwave background was predicted in the 1940s and detected accidentally in 1964. These were not failures of science. They were the natural pacing of a discipline that refuses to accept less than evidence. The question of black hole cosmology is likely to require a similar patience. The tools that might resolve it are either recently built or still under construction. The James Webb Space Telescope has been operational for only 3 years, and the analysis of its data is still in its early phases. The DESI survey is ongoing. The Euclid telescope, launched in 2023, is beginning to produce the large-scale structure maps that will test dark energy models to unprecedented precision. The next generation of gravitational wave detectors, LISA, the Einstein telescope, the cosmic explorer, will probe the primordial gravitational wave background at sensitivities far beyond current instruments. Over the coming decades, these tools will generate data that bears directly on predictions of black hole cosmology. The rotational asymmetry in galaxy distributions will either be confirmed or refuted by independent analyses. Dark energy will either be shown to vary with time or to remain constant. Pre-bound signatures will either be detected in the gravitational wave background or be constrained to be smaller than the hypothesis predicts. The theory will either accumulate support or accumulate falsifications, and the community will respond accordingly. Science is patient. It does not require dramatic announcements. It requires sustained attention, careful measurement, and the willingness to change one's mind when the evidence changes. The question of whether we live inside a black hole is currently in the category of not yet answered. It is not in the category of answered yes. The evidence is suggestive but not conclusive, and it is not in the category of answered no. No decisive falsification has been produced. It sits in a large middle space where most of the genuinely interesting scientific questions live, being worked on, being argued about, being slowly approached by instruments of mathematics and the collective effort of physicists who find it too interesting to leave alone. The final meditation. You have been inside this question for a long time now. Step back from it, for a moment, not away from it. Just back, far enough to see the shape of what we've been doing. We started with a night sky, with the vertigo of looking up and suddenly feeling the depth of it, rather than just the beauty. We followed a question, one of the most audacious questions physics has ever seriously considered, through its mathematics and its observations and its controversies and its open edges. We met Patria, who noticed a number. We met Smolin, who built a theory of universal evolution. We met Poplawski, who found a balance in the mathematics of torsion. We met Bekenstein and Hawking, who discovered that black holes have entropy, that they glow, that the information they contain is encoded on their surfaces. We met Meldesena, who showed that a surface and its interior can be descriptions of the same reality. We looked at 263 galaxies in the deep universe and found that 2/3 of them rotate the same way. A result that, if it holds, says something profound and strange about the structure of the earliest cosmos. And now we are here, at the end of the question, which is also, as all good questions are, the beginning of another one. Here's what the science actually says, stated as cleanly as possible. The universe may have begun as the interior of a black hole in a larger space-time. This is a serious hypothesis, proposed and developed by serious physicists, with mathematical support, and with several observational predictions that are either consistent with current data or actively being tested. It is not proven. It is not the consensus view of cosmology. But it is not a fringe idea, and it is not a metaphor, and it is not going away. The universe contains black holes. Each of those black holes may, if the hypothesis is correct, contain a universe of its own. We cannot confirm this. We cannot deny it. The event horizon, if it surrounds our universe, is not a cage. It is the boundary of everything we will ever know. But everything we will ever know is already, by any reasonable measure, an astonishing amount. Stars, oceans, language, music, the particular quality of light at the end of a summer afternoon, the way a question, seriously asked, opens into a space larger than the question itself. There is a word in physics, covariance, that refers to the property of physical laws remaining the same regardless of the reference frame in which they are described. The laws of physics do not care where you are standing when you observe them. They are the same inside a black hole as outside. They are the same in our universe as in any universe that might be described by the same fundamental equations. If we are inside a black hole, the laws of nature that govern us are the same laws that govern the parent universe. The same mathematics, the same logic, the same relationship between cause and effect, between evidence and conclusion, between question and careful answer. This is perhaps the most reassuring thing you can take from a night spent thinking about whether the universe is inside a black hole. Not that the question doesn't matter. It matters enormously. Not that the answer is comfortable. It is, in some ways, deeply disorienting, but that the tools we have for approaching it, careful observation, mathematical reasoning, the willingness to hold uncertainty without either collapsing into certainty or retreating into indifference, those tools work here, too, as they work everywhere. The question is open. The night outside is still dark. The same stars that were there at the beginning of this journey are there now. The same photons of ancient light, arriving after thousands of years of travel, striking the same retinas, producing the same vertigo of looking up into a depth too large to hold. You are quite possibly inside a black hole. You are certainly on a small rocky planet orbiting a middle-aged star in a spiral arm of galaxy that is one of 2 trillion in the observable universe. You are made of atoms forged in stellar cores, assembled over billions of years of evolution into a form complex enough to ask where all this came from. You will not receive the answer tonight, but you know the question now in a way you did not before. And that is not nothing. In a universe as strange and as large and as old as this one, a question clearly understood is already a kind of progress. Rest well, the universe will still be here in the morning. And so, almost certainly will the question.